This is chapter 3 of Engineering Calculus 1. Chapter 3 is about the derivative. So here in this chapter, we will be discussing the notions of derivative, a derivative as a slope, a derivative as a rate of change, and afterwards we will be discussing the derivatives of algebraic functions, the chain rule, and the general power rule. Then we will also tackle the higher order derivatives and then the implicit differentiation. So the process of taking a derivative, we call it differentiation. What's a derivative? So first, the notion of derivative. So we will define derivative with two different ways. And these definitions was derived by two separate scientists named the Wilhelm Leibniz, Gottfried Wilhelm Leibniz, and Sir Isaac Newton. So they developed this calculus, this derivative, to solve two different reasons. For Leibniz, this is to solve the tangent problem, the slope of a tangent line. Then for Isaac Newton is to settle the problem of orbits of planets that Kepler could not give a logical reasoning for its claim. So here we will also define derivative of those two things as a slope and as a rate of change. So first, as a slope. If you remember, what's a slope? A slope is it's the steepness of a certain line. So how steep the line is. In calculus or in pre-calculus or even in high school analytic geometry, we define slope as the ratio of its rise over run. It's if you have a line here, you're given 2 points. You need at least 2 points to solve for the slope. That's the general rule in analytic geometry. So this is x1, y1, and this is point x to y2. If I want to determine the slope of this line, it's just equal to y2 minus y1 all over x2 minus x1. Or this is rise over run. This is the rise and this is the run. This is rise and this is run. Or it can also be called delta y over delta x later on. That's one way of determining the slope of a line. We can also determine the slope using its equation or the standard form, the slope-intercept form, y equals mx plus b. This is the most used standard form, standard equation of a line, where m is the slope and b is the y-intercept. And another way to determine the slope is if you're given an angle, the angle of elevation or angle of elevation of the line. It's the angle of the line with respect to the x-axis, the smaller angle. And to do that, you need your trigonometric identities or SOHCAHTOA. You draw a triangle. So if this is theta, this is also theta here. So in trigo, if I want to determine, if I divide the opposite side of theta, opposite side is the rise. If I divide it with the run, which is the adjacent side, so opposite and adjacent, so that's TOA. So this will be equal to tangent theta. So another way of solving the slope is this equal to tangent of the angle of inclination or theta. So that's another way of solving the slope. Now the problem is, what if you are only given 1 point? You're not given an equation, and it's not a straight line, it's a curve. Yeah, it's a curve, it's a function, not necessarily a straight line. Then I want to determine the slope at a given point. That's in just 1 point. So for example, if this is the curve, I want to determine the slope here. So to determine the slope at that point, you just need to determine the slope of the tangent line. How do we do that? We are only given 1 point, so we cannot solve the slope of the tangent line. But using calculus, we can do that. So here, to do that, we need, if this is our function f of x, I want to determine the tangent, the slope of the tangent line at 0, 0. So what's the tangent line? It's actually the x-axis. The slope of the x-axis is 0. I want to determine that given only the point 0, 0. Okay, so in this example, but in general, it's not just the x-axis. It can be anything that is in tangent with the function. So if this is f of x, the red function, then the green point, I'll call it point P. And this black point here, let's call it point Q. So now, this line here, this block, this is called the second line. Second line. But we want to solve the slope of the tangent line. So we can solve for the second line actually because we're just given 2 points, point P and point Q. So what we do is we move point Q towards point P, the green one. So if I move this one, what happens? As point Q approaches point P, the slope of that second line is also approaching the slope of the tangent line. So we are still given 2 points here. So if you can observe now, it's very, very close to the x-axis. Our second line now is actually now in parallel with the x-axis or the tangent line. So if we make it very, very close with point P, we can say that the slope of that second line is also very, very close to the slope of the tangent line. Another way of saying that is when point Q is approaching point P, approaching, it's very close, but it's not the same, it's approaching. What happens is the slope of that second line is also approaching the slope of the tangent line. So we can use this concept to determine the slope of the tangent line. We can make Q very, very close to P. How do we do that? So in this figure, we just let it, the distance between them will be delta x. It's the x-axis. So we just call it delta x. As delta x approaches 0, that's the distance between point P and point Q, then this slope is also approaching, the slope of the second line is also approaching the slope of the tangent line. So if delta Q, Q approaches P, then delta x is also approaching 0. So this concept now, if we write it, m of the tangent line, you want to solve the slope of the tangent line, is now equal to the slope of the second line. This is only true when delta x is approaching 0. So how do we write that? When something approaches 0, and we just take the concept of limits. Concepts of limits. Limits approaching. So the limit of the m, the second, slope of the second, when delta x is approaching 0. When the slope of the second line, when delta x is approaching 0, is actually equal to the tangent line, the slope of the tangent line. And this is just equal to the limit of delta y over delta x as delta x approaches 0. This is the very, very concept of derivative of the calculus as a slope. And this definition, this is actually what we call this limit of delta y over delta x. As delta x approaches 0, this is what we call the derivative. The derivative of y with respect to x. So our notation will be d, meaning it's derivative of y with respect to x, dy dx. and dy dx is just equal to the limit of delta y, change in y, with respect to the change in x, or that's just the slope when delta x is approaching 0, or dy dx is just equal to the slope of the tangent line. So if you want to determine the slope of a tangent line, you just take the derivative of that function with respect to x. And you just need to substitute the value of x to solve for the actual slope of the tangent line. Now, we want to change our notation to in terms of delta x here. So if this is our graph, this is the function, this is point Q, and this is point P. If I want to determine the slope of the second line, given the points, so let's call this one x1. Then if this is f of x, then the y value will be f of x1, and for point Q will be x2 and f of x2. But I want to insert delta x here, so let's just draw a triangle here for the slope, because we're solving for the slope of this second line here. This will be delta x, the run, and the rise will be delta y, so that the slope of the second line is delta y over delta x. Now, what will be delta y? What will be delta x? So m second. This is just equal to delta y over delta x. So what's delta y? Delta y is y2 minus y1. Here, this is our y2, and this is our y1. And this is x1 and x2. But here, x2 is actually equal to what? It's actually equal to x1 plus delta x. Or we can just make it general. Let's just remove the subscript 1. If I call point P at point X, and the y or the coordinate is f of x, then point Q is at x plus delta x, and the ordinate will be equal to f of x plus delta x. Then we need to substitute this one here. Our y2 will be this one. This is our y2, and this will be our y1. Then so this is equal to y2 minus y1 all over x2 minus x1. So the second slope of the second line now will be equal to, what is our y2? It's f of x plus delta x. Then minus y1, our y1 is this f of x. Then we divide it with x2 minus x1. x2 minus x1 is just equal to delta x. This is our x2, and this is our x1. So if we subtract them, magka-cancel out. X will cancel out, so the remaining will be delta x. So this is the slope of the second line. We can make this one be equal to the tangent line if we take the limit of this as delta x approaches 0. So the slope of the tangent line will be equal to this one when the limit of that one as delta x approaches 0. F of x plus delta x minus f of x all over delta x. So this is the definition of the derivative, dy dx. So if you want to take the derivative of a certain function, you just take f of x plus delta x, you subtract it with that function, and you divide it as delta x approaches 0. You take the limit of that as delta x approaches 0, and you already know how to take the limit. Now let's take an example to illustrate this one. So remember this is the definition, basic definition of a derivative. So in your module, we have there an example we want to determine the slope of a tangent line. Determine the slope of the function y equals x squared at point 1, 1. I want to determine the slope of y equals x squared at 1, 1. So to determine the slope of the function, we just need to determine the slope of the tangent line. And how do we determine the slope of the tangent line? We just take the limit, use this definition. So first, we need to determine what is our f of x. F of x is just equal to y, so this is just equal to x squared. Next, f of x plus delta x. We need f of x plus delta x. So how do we do this one? We just use the concept of combination and composition functions in chapter 1. So we already did this one, so you should know how to do this. And this will be equal to, you just replace all the x with x plus delta x. So this will be x plus delta x squared. Composition. And to simplify this one, if you want to simplify, because we know x, we can actually substitute the value now. Directly substitute the value because we know x. X is equal to 1. So this will be 1 plus delta x squared. And if f of x is also equal to 1 squared, or is this equal to 1? So here, f of x plus delta x now will be 1 squared. We expand this one. Remember the expansion in algebra, a plus b squared is equal to a squared plus 2ab plus b squared. A is 1, so 1 squared, plus 2 times ab. A is 1 times b is delta x, so 2 times delta x. 2 times 1 times delta x. Then plus b, or b is delta x here, so delta x squared. So that will be f of x delta x. F x plus delta x. So to solve for the slope will be equal to the limit as delta x is approaching 0. So what's the formula again? It's f of x plus delta x minus f of x. So what's f of x plus delta x? This one. So we have 1 plus 2 delta x plus delta x squared. Then we need to subtract what? Subtract f of x, which is equal to 1. Then you divide this one with delta x. Then take the limit. So before you take the limit, because you have a denominator here and it's approaching 0, we need to simplify first. So how do we simplify? We can cancel that. 1 minus 1 is 0. So this will be equal to delta x approaches 0. 2 delta x plus delta x squared all over delta x. So here we can cancel out delta x, and another delta x here. So the remaining will be just 1 delta x. So this will be the limit of the 2 plus delta x as delta x approaches 0. And what's the slope now? So we just make this one 0 because it's approaching 0. So the slope is equal to 2. So the slope of the line at slope of the function at point 1, 1 is just equal to 2. So that's how we solve the slope of a tangent line given point. Let's take another example. Determine the equation of the line. So this time around, we will be determining the equation. Determine the equation of the line that is in tangent with the curve y equals 2 plus 2x minus x squared plus x cubed at point 0, 2. So I want to determine the slope or the equation of the tangent line. It's not just the slope, but we want the equation. So to determine the equation of a line, there are different ways. We can use the different standard form or the general form of a line. But in our case here, we're given a point, 0, 2. That's given. So what are the other given? The other givens are the curve, which is in tangent with that line. So from that, what can we get from that curve? We can get the slope, just like what we did in the previous example. So we have now, if we can solve for the slope, then we have the point. So what standard form will be the slope-intercept form or point-slope form? It can also be the point-slope form. But in this case, because this is 0 and 2, so obviously, if the abscissa is 0, then your ordinate is equivalent to your y-intercept. So we can actually use the point-intercept, which is y equals mx plus b. Our b here will be just equal to 2 because at point 0, 2, or here 0, 2, the function is 0 when x is equal to 2. Or the function is 2 when x is equal to 0. So we only need to solve for the slope now. And we can do that using the definition. M equals the limit of f x plus delta x minus f of x all over delta x as delta x approaches 0. So what is f of x? F of x is just equal to 2 plus 2x minus x squared plus x cubed. Or if you substitute now the value f of 0, because at point 0, 2, x is equal to 0. So here, f of 0 will be 2 plus 2 times 0 minus 0 squared plus 0 cubed. So f of 0 is just equal to 2. That is f of x here. Then for f of x plus delta x, f of x plus delta x, this will be 2 plus 2 times x plus delta x plus or minus, it should be minus x plus delta x squared, then plus x plus delta x cubed. Then simplify this one. You can simplify this one. You can expand x plus delta x squared and cube. So first we determine f of x delta x. Okay. Expand that. Or we can make it, or for us to expand it easier, because we know that x is 0. We can just make it 0 plus delta x. So this will be 2 plus 2 times 0 plus delta x, or it's just delta x, minus 0 plus delta x, or that's delta x squared, plus 0 plus delta x, or that's delta x cubed. And this will be our f of x plus delta x. So the limit, the slope now will be equal to the limit of f of 0 plus delta x minus f of 0 all over delta x as delta x approaches 0. So here, what is the f of 0 plus delta x? It's 2 plus 2 delta x minus delta x squared plus delta x cubed. And we subtract f of 0, which is equal to 2. Is this equal to 2? Then you divide it with delta x. So here we can cancel out 2. 2 minus 2 is 0. Then we can cancel out delta x here, delta x, 1 delta x, and 1 delta x. So this will be squared, that will be equal to 1. So simplifying the limit as delta x approaches 0 now will be equal, this one is 2, delta x over delta x is 1, minus delta x raised to 1 plus delta x squared. And taking the limit of this one as delta x approaches 0, so our slope now, this will be 0. 0 squared is still 0, so the remaining will be 2. So the slope now will be equal to 2. Then to solve for the equation of the tangent line, the equation of the tangent line will be y equals mx plus b, y equals mx. Our m is 2, so this will be y equals 2 mx 2x plus b. Our b before is 2. Or if you want it to be in general equation, so you can put y at the right side, so this will be 2x minus y plus 2 equals 0. So this is in the general form. So that is the equation of the tangent line at point 0, 2. So we solve for the slope and we substitute it into the y-intercept form. Then we convert it into general form. If you want it to be in general form. Okay, so that's how we solve for this slope of a tangent line of a given curve. Later on in the applications, we will also discuss more about this one, but we will not be using the concept of limit anymore, but we will be using the formulas that we will be deriving later on in the next sections.